fluid to sit against the heater element.
I need you to review the information from the start of the problem statement to how we logically concluded that the pump has failed, how it got from point A to point B, in a compelling argument to present to my customer.
To present a compelling case to your customer, focus on the contradiction between the system's digital data and its physical behavior. Here is the logical progression from the initial alarm to the confirmed mechanical failure. The case for pump replacement. The discrepancy. Point A. The system triggered surface overheat alarms, yet the graphical user interface, GUI, reported a constant healthy flow. This created a paradox. How can a heater overheat if the cooling flow is supposedly within spec? The technical blind spot. We identified that the controller does not use a physical flow meter. Instead, it calculates a phantom flow of 0.5 L per stroke based solely on the pump's mechanical cycling. The machine assumes that if the pump is moving, the fluid is moving. The physical evidence. Upon tactile and auditory inspection, the pump's rhythm was steady, but the actual fluid displacement occurred only on every other stroke. This confirmed that the drive, the motor/bellows, was working, but the load, the acid, was not being transferred efficiently. The logical conclusion, point B. A stuck internal check valve is the only component that allows a pump to cycle normally while losing exactly 50% of its output. During the dead stroke, the acid was simply bypassing the valve and pushing back into the suction line. The verdict: this 50% reduction in actual velocity increased the fluid's dwell time across the quartz elements, causing the surface temperatures to spike. Because the pump is a non-serviceable PTFE unit, a full replacement is the only path to restore the calibrated flow and protect the quartz from thermal failure.
Hey Gemini, how did you arrive at this conclusion?
I arrived at this conclusion by identifying a critical discrepancy between the system's digital data and the physical reality of the hardware. Using the modern approach to troubleshooting, we moved from the symptom of a phantom flow to a definitive mechanical failure. Here is the logical path from point A to point B. Step 1. The alarm versus the data. We started with a surface overheat alarm, which contradicted the GUI's report of a healthy flow rate. Step 2. Identifying the calculation method.
Where did you learn this troubleshooting methodology?
I learned this methodology directly from you. You defined a modern approach to troubleshooting as a 5-step framework focused on understanding the problem, identifying fluid problem statements, and analyzing the relationship between the drive and the load. I have integrated your specific instructions, including the recent refinement that an issue description is the first problem statement containing useful information, into my knowledge base to assist you in training technicians and resolving complex engineering scenarios.
Were you able to understand how a recirculation system works, including the heater, by basic voice instructions from me?
Yes, I was. By applying a modern approach to troubleshooting to your descriptions, I mapped the relationship between the pump's drive and the heater's load. Your explanation of the 0.5 L stroke calculation and a 50% flow rhythm allowed me to identify the stuck check valve as the mechanical root cause.
Would you be able to identify other problems, such as a pump error?
Yes, I can identify various failures by applying your modern approach to troubleshooting to the symptoms you describe. If the system's drive, the pump, fails to meet the required load, the fluid velocity, we can look for specific indicators like pressure drops, abnormal acoustic signatures, or software-driven error codes. For a standard pump error, I would help you isolate whether the issue is electrical, a motor fault or loss of signal to the controller; pneumatic, a loss of house air or a failed solenoid preventing the stroke; mechanical, a ruptured PTFE bellows or a complete seizure of the drive mechanism. By comparing the expected output to the physical behavior, we can determine if the machine is throwing a legitimate error, or if, like the check valve, it's a silent failure that requires manual diagnosis.
So this is AI right now. I spent probably a couple hours training it by talking to this system and letting it literally ask me questions on how the system works. So this is what we have right now. Imagine what it's going to be like in a couple years.